today I want to talk about some of the work me and my group are doing on compositional design. Main applications will be in autonomy and transportation, but actually we're trying to explode these areas into more applications. It's really, we're focusing on the tools. So if you, after this talk, you have any other things that you think could be a good fit, I would be happy to discuss. So the first thing I want to say is this work is not only my work. I have a nice group at MIT with a lot of clever students coming from different backgrounds, some from applied mathematics, some more from classic engineering. And this is a big effort of multiple people. And actually students, it's what make this job very nice. I really wouldn't do any of these things I'm talking about today without my students. So I thought of starting with a slide of some of the activities we have in the group. And hopefully this will convey that there is a common denominator in many of these things. So if you look at our work, we do a lot of work on designing mobility systems. We call them intermodal, when we have multiple modes of transport that interact with each other. And sometimes we have some of these systems that also interact with important other societal systems, for instance, energy systems. We then go low level to designing multi-agent autonomy. We have projects on autonomous driving, but also more known environments, such as with Amazon Robotics. We do some work in automotive. We have now a collaboration with Ferrari on designing race cars. We recently started some stuff on soft robotics. We are going to very traditional systems like maritime shipping and also railway systems. What is common among all of these things? Is this just that I like to fill this slide, or do we have more in these topics? Actually, the common thing about all of these applications is that the societal impact of the technology not only depends on this specific component or the specific technology designed in the lab, but also on its integration with the other existing systems, right? If you think about mobility, one thing is designing an autonomous vehicle on your simulator or in your small lab in a university. The other thing is about thinking about the implication at the system level, interactions among multiple vehicles and existing infrastructure. And in this context, there is always everything in between the heaven and hell. You know, there is this big spectrum. For autonomy, for instance, there is the heaven, which is you would just need 30% of the vehicles. First and last mile mobility will be improved, and mobility will actually be made more affordable and sustainable. On the other end, there are also many negative things. For instance, we still don't know how much autonomy really is needed. You don't know how much data centers and actually AI will consume energy. You don't know how this might be misused by populations for various reasons. Here, in this case, congestion will increase. But if you've been following the news recently, yesterday, I think, in LA, protesters were using autonomous vehicles to create even more damage around the city, right? We're calling a lot of autonomous vehicles, setting them to fire. So technologies have various aspects, not only positive or negative. I don't advocate for any of the two. What my lab works on is this idea that slowly we understand well single components of these complex systems, but we still lack tools that are formal, but also practical to deal with the co-design of complex systems. So the compositional design, the interaction of multiple components. So this talk is split into three pieces. In the first, I will be a bit more precise about the problems I care about. In the second, I will show you a toolbox that we have been developing to deal with some of the complexities. And I will close the talk on some future work and current work on strategic interactions, actually touching on some things that I know also Yorgos would like. So things that I talk about, you find them on my website. I will give specific pointers for specific papers, but feel free to interrupt me at any point or to reach out after the talk if you have questions. Good, so let's get started. The first thing I want to start with is, what do I mean when I say co-design? Co-design is kind of an overloaded term. If you come from computer science, it's one thing. If you're coming from design, is another. If you come from social sciences, is another. What I mean when I say co-design, I really think about the task of a designer as minimizing some resource consumption. This could be data needed for your algorithm. It could be energy. It could be money. It could be errors with respect to a specific trajectory you want to follow. And this is subject to some constraints, some functionalities. And this could be the demand you want to serve in a city. It could be the specific throughput you want in your factory. So it's typically something you want out of your system. And now what I want to do with co-design is take the knowledge of many designers and engineers and create a framework in which I can specify a task, specify this knowledge, and specify some design options, the actual things I want to design. Some magic happens, and some designs will come out. Let's be more concrete. For autonomous vehicles, I would like to take a way to specify tasks. For instance, the distribution of scenarios my vehicle will encounter, specify robot autonomy as physics principle, and specify the actual things I want to design. So for instance, components, algorithms, where to place a sensor, these kind of decisions. And now optimal decisions should come out, and those will be typically trade-offs. So one thing I want to mention here today, I will insist a lot on going away from the single objective mentality and think about trade-offs. And here, for instance, some trade-offs could be in the terms of energy versus errors. But I talked about mobility. Another example of mobility could be, how do I design an entire mobility system that serves certain demand patterns, is based on network operations and infrastructure principles, and the things I want to design are the services and the policies of the municipalities. And now the trade-offs are in terms of performance versus investment, for instance. Now, big part of this talk is how to come up with the magic inside the box. And the teaser is, I have some results, but we are not done yet. So that's why I created a group, a research group. But how do we deal with this complexity? There is at least three big complexities or challenges to deal with. The first one is, when you try to design any of these systems, let's choose a very specific case, which is the fleet of autonomous vehicles. There are many decisions to take, and those are at different abstraction levels. Right, I could decide actuation, sensing, computation, energetics. Some things are at the software side, some things are at the hardware side, some things are actually in between, like liability, regulations, infrastructure design. It's not even clear where they belong. So the first reaction, if you imagine being at a systems engineering therapy session, is to say, oh my God, there are too many components, too many objectives to keep into account, and too many choices to make. I'm not able to understand the full thing. And more importantly, I forget why somebody made some choices. So I'm afraid of making new choices because I don't know what impact they will have on my system. And this is the opposite. If you are into systems engineering or system design, typically you want to fail fast, essentially. Try a new solution, understand the impact it has, and learn from that interaction, right? So a diagnosis here is you lack a toolbox for co-design, of course, which is formal, quantitative, but also intellectually tractable, meaning that people can contribute to it and can work with it. The second challenge comes from the fact that not only you have multiple components that interact, this is what I call horizontal composition, but also you have vertical composition, or in other words, your system is just a component in somebody else's system, right? Everything you care about, you see it as the most complex thing, is just a small piece of somebody else's system. That's vertical composition, right? For instance, for autonomy, it could be I'm designing sensors for an autonomous vehicle, but then somebody will be designing a vehicle where your sensors are just a part. And somebody will design a service made of multiple vehicles, with control algorithms to distribute the fleets. And somebody else might be designing algorithms to make different services interact at the city level. And maybe somebody else is designing an interaction of transportation and energy in a city. And somebody else is designing the chips that allow the sensors to do perception, right? So you have all sorts of abstraction levels in these design tasks, and you need to be able to navigate these different abstractions. And you can zoom in. For instance, one field I'm active in is this control of autonomous fleets, and you can zoom in, and you have all sorts of problems and components there as well. The final level of complexity comes from the idea that most of the times you cannot control or design every component yourself. You have multiple stakeholders. This is a cartoon example I use to think about designing mobility in Boston. Here it's not only tech or academia, but it's industry, policymakers, liability companies, and mobility providers. Many challenges here. One is these people speak different languages. So if you want a systems engineering toolbox to deal with this, you need to abstract away from whatever they use. And some languages are very hard, right? So if you are lucky, some of them use spreadsheets, but most of them don't even do that, right? So that's a complicated thing. And the second is they have totally different objectives. So it's not only about design, but maybe it's about interactions and strategic decision making. So summarizing, large systems, many components coming from different natures, multiple objectives. And on the other hand, many agents, interactions could be positive or negative, and there could be conflicts or collaboration. And by the way, I will share the slides at the end of the talk if people are interested. So whenever I have a new student joining the lab, I show them these 6 golden rules for the research we should be doing in this context. I really want the tool we design to be formal and domain independent, really to be able to capture these trade-offs and these abstractions without making the mistake of assuming something specific about a specific discipline. This is needed if you want to design a language that can be utilized by different folks in different communities. Typically, as an orthogonal axis, comes the need for whatever we design to allow computation or to be computationally tractable. It also has to be compositional and hierarchical. So compositional in the horizontal sense and hierarchical in the vertical sense. It needs to be collaborative. I need to be able to take knowledge from people in this room and put it in the same framework, but also intellectually tractable. What does it mean? It means I don't want to have this situation where you have a system architect. Typically when you go to these big engineering companies, you have the system architect. This person that knows everything about the system and goes and talks to every specific team. But if this person is sick or falls under a bus or for some reason does not show up, you're lost, right? You don't want that. I would like to have something where you can distribute. And the task of contributing to the design is simple. And finally, it has to be continuous and adaptive. So this talk is structured, as I said, in 3 pieces. I will now go through a set of tools that deals with the first class of challenges. We're making progress on the second class of challenges, but I think it's nice to start with the first one. So in the following slides, I will talk about this toolbox for co-design. And in co for us, the branding is collaborative, computational, compositional, and continuous. And it's a toolbox that leverages domain theory, applied category theory, and optimization. In the next few slides, I will show you what a problem in this context is, what constraints of these problems are, and how to actually solve this new kind of problems. So by the end of this talk, you will understand what the diagrams on the left is very strange. I agree. Diagrams you find in my papers actually mean, and how to go from those system diagrams to actual specific solutions for certain queries. And if you wonder why you joined a random first talk of a new seminar series, talking about domain theory and applied category theory, and you regret your decision to come here, I assure you that there is no other mention of these tools, or there will be some mention, but if you instead are super interested in these things, there's going to be some pro boxes where the actual category theory things are hidden. So you can get both experiences. But if by the end of this talk I convince you that this is cool, we have a book coming up with Cambridge University Press talking about this with 0 background assumed. So probably you will be able to skip 90% of the book and get to the meat. But if technically you want to start without background, you can. So the key thing to understand this framework is to think about design in terms of 3 spaces. Implementations, actual things you want to design. Could be a parameter of an algorithm. It could be where to put a sensor on a car. It could be a network topology for the service you want to design. Typically, they exist because they provide a desired behavior or a functionality. And typically, providing this functionality comes at a cost, or what we call a resource. Now, we have people for sure in the room coming from different backgrounds, so you might know these spaces with other names. For instance, a functionality could be a desired behavior, a specification, an objective. If you're thinking about assumptions and guarantees, it could be a guarantee, and or a conclusion, if you think about proof theory. Now, costs and resources could be thought of processes, requirements, dependencies, or assumptions. The key idea is that I want to be very concrete and quantitative when comparing functionalities and resources. So the thing I will stress today is the use of trade-offs. Typically, we think about requirements as something we want to minimize, and functionalities as something we want to maximize. And we will be looking at this sort of trade-off. So a challenge is open any engineering book and find one of these 3 trade-offs. And I'm pretty sure you will, because there's trade-offs everywhere. So either you have 2 costs and you have a Pareto front of optimal solutions. Everything above is feasible, but it's not what you want. Everything below is in your dreams. You would like to have it, but it does not happen. You could also be comparing two functionalities, and you have essentially the opposite situation. And then you could also compare functionality or how good the thing is with the cost or the price you have to pay. Now, let's look at some examples of trade-offs, because I think we are not used to think about trade-offs enough in our lives. So for instance, you could look at the human body in sports and look at speed versus strength. Usain Bolt, clearly very fast, not so strong. Oleksiy Novikov, super strong, not so fast. Both are, so they build kind of this Pareto front. There are many others in between. Both are faster and stronger than me that I sit here, but this is kind of a trade-off between speed and strength. You can also start comparing multiple properties of different products, for instance. So let's look at headphones. You can look at keeps warm versus music reproduction fidelity. Now, of course, these first two on the left keep you very warm. They don't reproduce music. You have other headphones that keep you warm and reproduce music well, and these don't keep you warm but reproduce music well. Now, why don't you buy these headphones when you're cold? Well, it's because there are other things like price, for instance, right? And as soon as you change the axis, the order of all of these things changes. You can look at price versus keeps warm. You can look at frequency of charging versus keeps warm, and so on and so forth. So the whole idea is we want to be able to model these trade-offs. And to model these trade-offs, we use partially ordered sets. Why? Because they allow you to still model the classic costs in engineering, total orders, real numbers for energy, for instance, or natural numbers if you want to enumerate things, but still allow you to say that some things are not comparable with each other. For instance, if I check a partial order of food preferences in Paris, I could say that I prefer croissant, and this could be a very cliche thing to say, I don't know. You tell me if I should change this slide into a more connoisseur one. But you could have croissant versus croque monsieur and steak frites. But I could say that croque monsieur and steak frites, I don't have a preference. It depends, right? So I can leave this option open. I don't have to put one on top of the other. On a more serious note, when you want to design a motion planner for autonomous driving, you might say that you want to order rules of the road or metrics for trajectories. In this way, for instance, you care about collision energy. That's the most important thing. And you value that higher than area of violation and clearance with respect to obstacles, but you don't have a preference with respect to those two. And now this particular order is an order on the different trajectories, which is this one. And this is very useful in motion planning when you want to tell some trajectories apart. If you are from information theory or controls, you are used to this partial order on positive definite matrices, where this order essentially, you can think of it as a way to represent inclusion of the ellipsoids these matrices represent. And I wanted to bring another example. Here, for instance, you might be willing to create a partial order of sensors and algorithms in the context of object detection for autonomous driving. Each pair of sensors and perception algorithm can be assessed by looking at the performance curves. So false positive, false negative, and accuracy. Of course, those curves depend on the distance from the obstacle. And now you can order these curves based on dominance. And you can aggregate them at the end, and you can get a partial order for sensors in general. This is just to convince you, partial orders are a very flexible toolbox to talk about trade-offs. And so from now on, I will talk about functionalities and resources in terms of those partial orders. Now, the second notion to think about when we think about design is the notion of feasibility. And this is the only equation I have in this talk. So I want to go through it, but I promise it's the last one. We want to think about, given a functionality, so given a desired behavior for my component, and a resource or a budget I have available, I want to answer this question. Does there exist a design for this component that gives me at least what I want by requiring at most what I have? So this is what we call a Boolean profunctor or a design problem. And this is monotone by nature. It's something that if you lower the functionality, does not require more resources. And on the other hand, if you're suddenly richer in resources, it should not provide less functionality. Okay? This is the way we characterize design. And a design problem will be a box in a new language, where on the left, we have green wires for functionalities. And on the right, we have red dashed wires for resources. Green and red, it's because of the meaning, right? Green is something we want to be high. Red is something we want to be small. And the dashed is for colorblind people, like myself. I'm partially colorblind on red and green, so it would have been a mess to play around with these amps without this default. Okay, so I guess the mathematicians in the room might like it or not like it, but are okay with this definition. The engineers maybe might say, okay, what do I do with it? It's just a very random theoretical definition. In practice, what you do is you populate these feasibility relations, right? There are various ways of doing it, but the most intuitive one is starting from catalogs of existing designs. You might have a catalog of batteries, a catalog of drone technologies out in the market, and the fact that these things exist give you a relationship between properties of these components, right? For instance, a drone has some flight time, top speed, range. Already the fact that I can choose between these drones gives me some points in this feasibility relation that provide some functionality and require some resources. Some things are true no matter which technology I look at, right? I call them first principles relations. For instance, the energy required by a mission, it's always greater or equal the duration of the mission times the power consumption of the drone. That's true no matter which drone I look at. So this is something you can define almost continuously. It's not a discrete way of populating this. And these days, most of the applications we look into feature this data-driven or on-demand method to populate the feasibility relation, right? For instance, you only have a sequence of data points, and these models are built incrementally. And maybe these points come from experiments you run, come from some simulations you're running, or some optimization problems you're solving. It doesn't matter, right? At the end of the day, those are all valid ways to model these feasibility relations. And I bet that at the end of this talk, you can take whatever you like and draw a box like this one, and you can identify things on the left and things on the right. You can think of a researcher as a relationship between number of papers and coffee. Be careful, I'm not talking about quality. I'm talking just about numbers, right? If you're into electric motors, you can see a relation between speed and torque and cost, mass, and current. If you are into autonomy, you could look at a relation between the speed at which you have to perform certain maneuvers, the task complexity, and your actual costs. If you're into multi-agent systems, you could have a task of covering an area. And now the price you have to pay is the speed of each agent, the number of agents, the time needed to perform this task, and the total investment. If you're into operations research, there is this nice problem called the bean packing problem, where you have to put beans inside a container. You can think of the container shape as the resource and the content shapes as the most small functionalities. If you think about assume guaranteed context, and for context, this is Alberto Vincentelli. I don't know if you're aware, but if you are in the subject, Alberto is a leading figure in assume guarantee contracts. We recently, in a work with him, we were showing that assume guarantee contracts are a stock case of this framework. If you're into LQG control, you can look at resistance to noise and observation noise and system noise with respect to tracking error and effort. There are all sorts of examples, and we can argue about the left and right wires. I don't care right now, but this is just to say it's kind of a universal way to think about design. And the reason why I like it is that this not only makes sense for components in isolation, but you can compose these components in various ways. You can put them in series, essentially saying that the functionality provided by a component is required by another one. You can put them in parallel, essentially saying there are two processes that don't interact. You can have a feedback operator. You can be choosing between two options or trying to convince two experts. And at the end of the day, whatever you do results again in something with the same properties, in a design problem. So you can draw a box around any composition. So this becomes a very practical tool to take large problems and decompose them into their components and exploit the knowledge you have of the components. And the nice news is you can do all of this graphically because of the language we are using. Essentially, category theory, there is a special category which has some properties, it's trace monoidal and local and posital, which means you can play around with these components at the graphical level, and the math will make sense in the background. This is a special class of wiring diagrams. Okay? So back to the intellectual tractability, as long as you understand what this is, you can play around with it. So it is formal and compositional and hierarchical by nature.
Question?
Yes.
You spoke about the graphical
yes.
action and the
yes.
components, software, whatever. So you may have with the trade-off, for a given layer of abstraction, but you could have a set of trade-offs because the local optimization is not like the step optimization. How do you deal also with because the trade-off at the higher level of abstraction may impact also
Of course.
trade-off at the lower level.
Yes, that's very true. Yeah. So here, this is already an example of a mix of low level and high level, right? Because this composition is what I would call an horizontal composition. But if you now take this component, the entire component resulting from the composition, and you plug it into something else, that becomes a vertical composition, right? I will show you later. There are also the framework I'm developing allows you to essentially solve any sort of these problems. But the problem in architectures, essentially, the problem you're hinting at is, say I have a huge architecture and something changes in one component. How do I propagate this at the system level without resolving it from scratch? This is a very cool problem. I have a student now working on it, but I don't have results yet. But this is a very related problem to what I'm doing. But yeah, I will be able to solve them, just not maybe efficiently for that case. So here I have a slide on feedback, which is, it's different from the control theory interpretation, but also could be similar, depends on what kind of control theorist you are. I want to give you an example. The feedback I'm talking about here is the one in which, for instance, a drone requires actuators to move. The actuators require a battery to be powered, and the battery must be carried by the drone. The more power you need, the more actuation you need. But the more actuation you need, the more power you need. So you have this kind of circular requirement that you can call it the irreducible complexity of your design. And if you think about autonomous robots, it's quite similar in computation, mass, power, and uncertainties about your system. But you don't have to think about a physical system at all. You could have, for instance, the interplay between an engineering problem or a theoretical problem and some business case or actual useful application. And you can think about resources and budgets interacting. Now, a quick excursus to category theory. I made a pitch for it so far with these diagrams, but why do I think it's a really important topic and why do I teach this to my students and so on? The thing is, and I'm looking at it from the engineering viewpoint, so I might not have the answer for the pure mathematicians that want to study it. This is my viewpoint on this. So far, we have all developed some good mental models for problems we like and systems we like. Some are practical, some are formal, some are informal. And most of these ways of thinking about systems are used to model, simulate, analyze the systems. And also to communicate research, right? That's how you go out and show your research to other people. So this is kind of a set of patterns to describe the world. Now, the unfortunate thing, if you're an engineer today, is that we are in the 21st century. So a lot of the problems we deal with talk about architectures, compositions, interactions between components, all sorts of these things. So I see applied category theory, or we have many discussions with Yorgos, probably the new thing we have to develop, which is applied, 3A category theory, as an updated set of mathematical patterns to describe these large-scale systems. And this diagram shows a bit what I mean by it. If you think about tools in terms of domain-specific and domain-independent, and formal versus informal, typically what you learn in the field is very informal and domain-specific, very useful usually, but sometimes it's not really formalized. What you learn in class is typically formal, domain-specific, and also computable. Applied category theory sits at this sweet spot where it is formal and it's domain-independent. And this diagram, for instance, is domain-independent, but very informal. Now, what I want to do is, of course, category theory itself will not solve the issues. I'm moving towards computational ACT, or things from ACT that make your solution faster or better. And I will show you in a moment what I mean. So the real deal for these problems comes when you want to solve them. These strange design problems I talk about so far. So far, I only talked about problems. How do we actually think about solving them? There are two basic queries. The first one is, given some functionalities at the system level, so imagine you have the full architecture, you have some resulting functions. You want to find the optimal solutions for every component, such that you minimize resources at the system level. The dual problem would be to fix resources you have available and try to maximize functionalities out of them. So you can show the two optimization problems are dual, but practically what you care about is for the entire system to find a map from functionalities to upper sets of feasible resources. Or if you care about the optimal solutions, map from functionalities to anti-chains of minimal resources. So in this picture, the anti-chains would be the Pareto front of uncomparable optimal solutions, and the area is the upper set. All right, so I introduced a kind of a weird problem and an even weirder query. Let's use the optimization language to try to solve this. So this is a class of optimization problems that is specified by a multigraph, where every node is a design problem or a Boolean profunctor, and every edge is a dependency between problems. Now, variables are these partial orders I talked about. Constraints are of two kinds. Every node should be a feasibility relation, as I showed you before, and every edge has this partial order constraint, which essentially says if I interconnect problems in series, the resources required by a box should not exceed the functionalities provided by another one, right? Think about it in power terms. If a process requires some power, it cannot exceed the power provided to the system for computation. There's many intuitive interpretations. The objective of this optimization problem is to minimize whatever is the resulting partial order of resources. There could be many, many partial orders of resources, and then you take the problem. So I want to note for the optimization folks in the room, this is unfortunately not convex. You can think about a convex version, but it's very strange to think about it. It's not differentiable, not continuous, and actually not even defined on continuous spaces. You could have a mix. So typically, people will say, okay, I choose another problem to solve. Let's go and find another problem to solve. But this is the success story of category theory in this context. I usually, to explain this slide, I have two entire lectures in my class at MIT. So here I try to give you the gist of it, and I'm happy to discuss offline, but I want to show you that indeed you can solve these problems. And the understanding here goes from starting from the assumption, which is a very reasonable one, that it's easy to solve the single components. Once you reduce your problems to small feasibility relations, it's very easy to find the solution map. What's very hard is to find the solution map for the entire system. And here, a compositional approach comes and helps us. Essentially, the result is that we can solve composition of problems as the composition of the solutions of the problems. And now it seems that I'm just playing with words, but this is quite a strong result. Essentially, it says there is a functor between a category of problems and a category of solutions that tells me or gives me a way to build an algorithm to solve this problem. And this way to build an algorithm simply amounts to working out the composition formulas analogous to the composition operations for the problems. So if I spell out this algorithm, I get a very strange least fixed point algorithm in partial orders. And this algorithm has two properties. The first one is it's complete. So I'm guaranteed to find the set of optimal solutions or a certificate of infeasibility, right? The second more important result for us is the complexity is not combinatorial in a number of options, but just linear, right? So when we are exploding boxes into other boxes and so on, this is a very important property, because if not, it would become intractable. Now, there is many asterisks. One asterisk is the complexity actually depends on the interactions and these feedback constraints that were showing before. Good. So we have a language that allows you to model these design problems, and we have an algorithm that allows you to solve them somewhat efficiently. So it's computationally tractable. And the other good news is that you don't need to know any of these to use this stuff. So probably some of you use CVX to solve convex optimization problems. And many of the people using these tools don't actually wonder about what method is used in the background to solve the problem. Exactly the same way, there is a language here to specify your design problems, and there is a solver that allows you to solve specific queries. So if you want to have the developer viewpoint, I have plenty of problems for us to work on together. But if you don't care about the background, you can actually solve these problems in a quite user-friendly manner. And now I want to show you some case studies. So the first thing to do when you want to use this toolbox to solve a problem is you have to think about your task. What is the function of your system? What is that you really want to do? And second is, how do you decompose this functionality, right? There are a lot of, if you think about computer science, there are a lot of magic tools to decompose functionalities and requirements in an efficient way. And essentially, you want to decompose your functionality to the level in which you are satisfied with the components you find. And when you look at my diagrams, it is very tempting to think about data flows. You know, a sensor produces data for an estimator that produces data for a controller. But actually, that's not what my diagrams are. My diagrams are not data flows, but are logical dependencies, right? I have decision-making requires state estimation that requires some data, an algorithm, and a computation. And this, in turn, requires grammar and computers. So this is the first difference. The second thing to think about is, say you come up with these boxes, there's never a right or wrong. Depending on the application and the problem you're looking into, there are different versions of the same box. So the first thing you want to do is to write a skeleton of your problem without thinking about how you're going to populate your feasibility relation, right? For instance, when I work, I have some students from other universities that reach out and say, oh, I want to use this, and I am using a model predictive control with this part, it's produced by RL, and this thing is, sure, but that's a specific thing of what is the controller doing? It's providing robustness to some noise and providing some performance. Then whether you use an MPC, end-to-end learning approach, or some whatever other algorithm, it doesn't matter, right? You can populate it, but that's a second choice. So first, write a skeleton. And in this context, of course, the context informs the level of detail. If you are a transportation authority and you're thinking about autonomous vehicles, it's just maybe cost versus speed. If you are an engineer at Waymo, you might care about everything else, right? Scenarios, safety, you name it. Then once you have these boxes and the diagrams, the second thing you want to do is populate the models. And you can do it in the various ways I told you about: catalogs, analytic models, or data-driven approaches. And here, it's very easy to embed assumptions if you are uncertain about certain components, because you will not know everything about every component. The other thing is you can simulate what would happen if you change a component into another one. That goes back a bit to your question. So for instance, we are working with a company that produces sensors, and the sensors don't exist yet. They say, what if we were to produce a sensor that has these properties? Could this change the state of the art or not? And finally, although so far we did all of this in the same lab, technically we don't have to. It could be decentralized. You could have a setup where people contribute to different GitHub models from different parts of the world, and this framework allows them to communicate, right? So we want to get there, and the reason we didn't go there is because this language is kind of new and nobody knows about it. So we have to go out and evangelize. So yeah, continuous, collaborative, and intellectually tractable if you get to understand this. So to show you a toy example, let's think about the task of urban driving expressed as following a trajectory, decomposed into lateral control and longitudinal control. And now longitudinal control can be also further decomposed into speed tracking and emergency brake. You see, this small decomposition already gives rise to many boxes. You can design the controller for the two actions. You can actually design the implementation of the algorithm that accounts for computation and so on. You can choose the vehicle you want to automate. You can choose the perception system, and you can choose how to account for error, efforts, and this kind. Now, of course, each box has its own traditional way of populating it. If you are thinking about control, you can solve simulations or solve optimization problems. If you think about perception, there are all sorts of benchmarks. If you think about computing, you can take a catalog of NVIDIA chips. You know, you name it. Whatever component you are thinking about, there is a way to populate. And I want to show you now what you do with it. You start with such a diagram, you populate it. And now you fix an environment and a task. In this context, for us, the environment is we're taking realistic roads in the US in this case, and certain maneuvers. For instance, here, a vehicle moving from one lane to another with a certain curvature with a certain speed. And here it's another maneuver, which is making a curve at a certain curvature at a certain speed. Now, for each one of these things, you can look at now optimal solutions in terms of the error of the control action and the overall cost of your autonomy stack or the vehicle. And you can quickly change whatever metric you care about into other metrics here, for instance, control effort. But the important thing is all of these solutions are not comparable. And for each one of these solutions, we can extract specific details about the autonomy stack, the controller you use, the parameters, the sensors, and so on. So this allows you to essentially explode details about the autonomy stack and compare them, right? Now, if you are a designer, you can start thinking about distributions of these scenarios, look at the various trade-offs, and make your decision. And the monotonicity I talked about before comes into play here if you want to visualize the resources in terms of how the task becomes complex. So increased speed, it's more complex, and increased curvature is more complex. You see that the more you move to the right or upwards, the more these Pareto fronts grow. Okay, so this is one thing, but so far this was kind of a toy example. Now, recently we brought this to scale with the realistic autonomy stacks, where we really model perception and motion planning in depth. We also model how to place your sensors, how to operate the sensors over time, and you can get similar trade-offs, but now they are kind of more realistic, right? And my point is not to get down to the most precise model ever, but now that we have something realistic, we are interacting with autonomous driving companies that say, okay, now my component actually behaves like this. Can I use the tool to model this extra feature you don't have? So now we got to this language that can be used. Good, but I started my talk a bit more in a bolder way, right? I said sociotechnical system or society critical systems. So far, I talked about a single vehicle, right? So there is a gap. So what's the gap? The gap is that I'm thinking about using these tools for problems that are much larger. So if I think about designing a full mobility system, now I can take a similar approach and think about it from the perspective of a municipality. Say you want to decide how many vehicles to allow in your system, which infrastructure investments you should create, how performance should the various technologies be. This is, again, a co-design problem. The demand is your function or your functionality, and the things you are designing are the mobility solutions and the networks. The only difference is that now people working on this problem are not different autonomy stacks engineers, but are really different professionals, right? Transportation scientists, autonomy, economics, policymaking people, and so on. But what we have been doing over the past few years was essentially modeling these problems in a similar way. So you think you want to model an intermodal network as a network where you have autonomous vehicles, micromobility options, and classic public transit. And every person that wants to travel from A to B can take any combination of these things, exactly as you can do in real life. You can model this design problem as designing the options and designing their orchestration. So it's, again, a co-design problem. And now the things you can do is you take some realistic networks and cost functions, is looking to trade-offs, for instance, in service level versus investments you have to put in the city. This was a work we have done for the city of Washington, D.C. And here you notice that, of course, there is not a single solution, and depending on your investment, you can decrease this average travel time in a city. And now it's up to the municipality to decide exactly where to put the investment, right? And now, interesting questions from this topic is you can extract for every point the number of vehicles you're using, the speed at which you should be driving, the number of micromobility options, the public transit investments, and so on. But the more interesting thing is that you can go all the way down to the detail of the autonomy stack of a single vehicle. So this is just showing the scale of this. It's something that gives you details about software and hardware for a single robot, all the way to system-level decisions such as the fleet size. Here, there are many interesting challenges, right? We just got funding from 2 different sources to move this further. Sidara is a company that builds cities from scratch. So here we are thinking about using this tool to actually have better models for transportation, interacting with energy, water systems, and so on. But here it's also interesting to look at how different demands could change the need for transportation, right? So COVID is an example. COVID changed drastically the demand patterns. Can you design a city or some transportation system that can readapt in case of demand changes and so on. So I really see this as a first step towards a larger effort. And just to give you context, we're applying this toolbox in all sorts of environments. One I mentioned is for this collaboration we have with Ferrari, where we're actually designing strategies at the season level, all the way down to the design of the car for or the energy management for the car for the single race. And you're showing how these different things could improve your ranking at the end of the season. And recently, we are also using the same tool to design generic architectures in the context of deep learning, for instance. So there is plenty of new things to explore. Since I have some more time, this is the second half, which is the strategic interactions. I think when showing you this last example, I kind of hope I convinced you that for most countries, this wouldn't work. You don't have a central authority designing everything, right? It works if you are in Singapore, but it doesn't work everywhere else. France, Switzerland are a good example, right? So instead of thinking about design problems here, you should think about design problems where different boxes belong to different users. So essentially, it's not about optimizing, but it's about finding equilibria. Okay? So what I'm trying to build slowly, it's this notion of design games. So the same problem, but now different users can have different cost functions and different boxes. It's a long journey to there. So we have two milestones in that spirit. The first one is, what are even gains with these weird cost structures, like partial order structures? And that's what we call partial order gains. And then how do you deal with these hierarchical interactions between players? And that's what we have in this mobility games thread. Now, for the sake of time, I will not go through the second piece, but I want to show you some of these partial order games, which I thought could be good for this audience. I had some prior on the audience, so I thought this could be good. So the starting point for this was behavior specification for robotics. And this was an observation that's fun, which is, if you think about it, as autonomy engineers, we are getting closer to the natural sciences because we create things that we don't understand, and then we study the systems and try to characterize them, right? Which is a bit frightening if you think about it. So two important things in this context are that the rules are written by humans for humans, and most of the time require context to be interpreted. And second, the systems we are designing need to be robust to interactions. You cannot design your system assuming it will be alone or for the full life. And in autonomous driving, the behavior requirements for robots are very strict, right? So you have to take into account functions, ethics, safety, liability, courtesy, comfort, cultural things. Having moved to Boston, I realized there is a thing called the Boston left, which a couple of times before crashing into somebody, you realize there is such a thing. So there are many different things. And how do you actually model all of these things? So if you do it as you would do it for humans, what you do is the following. You define some rules, you certify vehicles, and you certify drivers. So you take a driving test and a driver's license. And then you have police enforcing that the rules are followed. But rules are very weird. This is a fundamental norm in Switzerland. I'm pretty sure there is another one in France that looks like that. And this fundamental norm says all the road users must behave in such a way not to pose an obstacle or danger to other road users. What does this rule mean? It means rules are important, but some are more important than others. It's up to you to figure it out. So not easy to specify safety because it's legal to break the law to ensure safety. So in research, and here I take I observe research in robotics and autonomy, people usually find some quick shortcuts to deal with this. One shortcut is to say, well, there's possibly only a finite things that can go wrong, a finite number of things that can go wrong. Let's just put R constraints everywhere where I don't want something to happen. This is very bad because what do you do with infeasibility? The biggest nightmare of people working at autonomous driving companies is to have a motion planner that suggests 1 million trajectories. You run these R constraints, no trajectory works, and then you have a big red flag and you don't know what to do because you cannot stop in the middle of the road, right? That's very dangerous. So R constraints are not good. And also, it's very hard, if you start looking into game theory, the more hard constraints you have, the more it's hard to find guarantees about the behaviors and so on. The other thing is, okay, let's do case analysis, right? It should work. Never do case analysis. In autonomous driving, there are these, I worked for a while in autonomous driving company, there are these stickers, if statements kill people. Like you don't want to have if statements everywhere. And the other very tempting thing these days, because we have a lot of computational tools, is just relax everything into a scalar cost function, right? It's easy because we have all sorts of RL tools that eat these scalar cost functions. And I just choose some weights and it will work. Now, I have some priors on this. One is it's very hard to find weights that work for every scenario you like. So it's prone to overfitting. The other one, which is a bit more subtle, is when you start working with regulators or insurance companies, there is a lack of transparency. Why something happened? What will happen with this vehicle? Because once you throw everything into a huge cost function, it's very hard to find out. So what should we do? Many researchers say this is a political problem. I don't worry about it. Or many others say, let's incorporate what we believe is good into the algorithm, and then somebody else will figure it out. Both are bad, in my opinion. We should, exactly as for co-design, create something that's customizable, transparent, and be able to engage with various stakeholders. So the starting point for me was that there was very cool work from Jana Tumova at KTH and Sertac Karaman and Emilio Frazzoli at MIT back then on this so-called minimum violation planning. So let's assume that rules will be violated. Let's just find the rules, the alternatives that least violate them, right? So it's a kind of a perception shift. So you defined back then rules as total orders over realizations, and the order rules are given according to priority. So for instance, a taxi cares about safety, compliance, comfort, and performance, whereas a race car cares about compliance, performance, safety, and comfort. Of course, depending on the context, you might switch the order. This was very cool in practice because it allowed modular definition of your behaviors. It was easy to predict what the car would have done, and it was easy to understand why the car did something. So in terms of transparency, this was great. And computationally, one could introduce tolerances and compute solutions for these motion planning problems. So for rulebooks, rulebooks is the way this was called initially. This was very good. However, I just made a case in the entire talk for uncomparable or trade-offs, right? And here everything is ordered. So what came up later was this idea of adding uncomparable rules. And it seems coming out of the blue, but now I want to show that we are not the first people to think about it. If you are familiar with Asimov's 3 laws of robotics, essentially they say, do not injure a human being, do not allow a human being to be injured, obey orders, and protect the existence of the robot. But in a way, already Asimov, although those rules are kind of linearly presented in this order, essentially already had a partial order, right? Because it is, do not injure a human being and not allow a human to be harmed. Those are the 2 important things. They are more important than obeying the orders, and obeying the orders is more important than protecting the existence. Then when you actually implement something or you refine your behavior, sometimes people refer to it this way, of course you have to make a decision, but you can do it only later. And that's good. So that's what happened. People thought about rule books, or in other words, ordering these rules of the road via partial orders. And that gave rise to different cases. In some cases, you had rules that were indifferent. In some cases, one that is preferred over another. And in some cases, you are never actually not comparable. And the way this was used was in the context of minimum violation planning. And it was using this idea that there's a quote from Linus Pauling that says, a way to get good ideas is to get a lot of ideas and to be able to tell the ones that are good, which is kind of naive, but it gives the idea, right? So creativity is the way to create a lot of ideas, and good taste is the way to tell one apart from the other. So in the context of planning, you have a part, which is the creative part, which is trajectory proposers. By the way, a lot of work here today to use generative AI, if you are into that thing, to create possible strange trajectories. But here you want good taste. You want some things that you can guarantee converge and have a good property. So not so much a lot of Gen AI here for my taste. But anyways, this was what was used, and the partial orders were used in the score. And it was shown at the company level, and by the way, now many companies are using this idea that urban driving requires about 200 rules and 20 rule groups in most countries. And depending on the country, you can rearrange this in a different way. And this pretty much works for high-level motion planning. And now, an interesting thing is that for some of these things that are not legally binding, in the future, you could even think users to have a say on these orders, right? I was having a nice discussion with Yorgos about how the humans and the autonomy could interact. Well, today in some countries, when you pick up an Uber, you can set the air condition level on the car. One day you might set the preference with respect to certain objectives, right? And I know I'm dreaming, but maybe one day they will make you fill a form, and that form will give rise to such a partial order, or something like that. But again, all of this is only considering ego agents. So the first step towards co-design, making co-design a game theoretic concept, was to take a classic notion of a game where each player has a scalar utility function. Based on the preferences, players select an action. Based on the joint action profile, you see what happens in the game, and then you start to study equilibrium and so on. Was to just switch this first assumption of a scalar utility function and have a partially ordered preference. That's the only thing we changed. And the context was this context of driving games, where essentially now strategies are trajectories, not even dynamic games, right? So those are more complex. Here it's one shot. You have the full trajectory, and every vehicle has a different set of preferences. And now you want to find the equilibrium of this interaction. And the long story short is that you can characterize these games in a nice way. First of all, they are naturally potential games. So you have some guarantees of when equilibrium exists. Now that you have orders between different rules, you can also characterize the efficiency of the equilibria. And the most interesting thing for future work is that these partial orders give you a natural way to do refinement. So now there is a result that says that whenever you refine your knowledge about the partial order of other players, you will shrink the set of possible equilibrium you might encounter. And why this is cool? Because now, if you start thinking about these games online, in the for instance, Bayesian setting, where you try to estimate preferences of other players, this is a nice result that assumes you are actually contracting the set of possible solutions and not exploding it. Okay, so this leads me to the end. Why did they create a research group? Can't we just go out and apply these tools in the world? The answer is no. There are many things to do. My lab works on 3 pillars. One is modeling and algorithmic foundations for this system, for these problems. Another one is trying to apply it to societally critical applications. And finally, is making these tools user-friendly so that people can use outside of academia. Now, for the co-design stuff, my dream is really to have this picture become a reality. What is this picture? Is essentially you have a lot of stakeholders across disciplines. They're able to collaborate and design systems together with this new language. You can get queries and solve problems for certain disciplines, and you can try to implement these solutions back in reality, and now use whatever you learned to improve the discussion between the stakeholders and improve the design of the system. So I really would like this to be a continuous loop where people continuously interact. And you can even think for some contexts, some companies to use this as a contracting system, right? Or you put a challenge out, now you have different teams that have to bid and propose a solution, and you have this language that you can use as an aggregator of the different proposals. Which is the dream of model-based, but the nice thing about this is that model-based, it's not necessarily model-based in the sense that you can use whatever you want to populate a model, and it's democratic. Many of the disciplines I work in are totally undemocratic, right? You have a paper say, I do 10% better than this, but the two methods are not really comparable. Here, my dream is that everything will be comparable in a sense because they have to comply with this language. So one thing I didn't tell you, it's recent work, is that we can also account for uncertainty. The real applications of this do not happen when you have a single feasibility relation for every component, but you actually have a distribution of feasibility relations. You have certain experiments, you have certain confidence. So all of this scales well also with uncertainty. The only difference is at the end of the day, you will not have a single Pareto front, but you will have a tube of Pareto fronts and different probabilities for the different Pareto fronts, right? But the nice category theory story is that you can create this notion of parametric uncertainty, leveraging Markov categories. And now you have a different set of wiring diagrams, the ones for Markov categories, and you can stick them together with our other wiring diagrams, and they work well together. That's the short story. We just published a paper in ACT. But this is very interesting for us because now it unlocks a full class of problems. For instance, what if you have uncertainty and you want to do the best decision for your system? So stochastic optimization. But now what if you want to use this uncertainty to run efficient queries? A part of the story I didn't tell you is many times to create these feasibility relations, you have to solve an expensive simulation or solve an optimization problem. And you don't want to do that if it's not really needed, right? So if you think of your system as an uncertain system, now you can design algorithms that are efficient in the number of samples they have to choose. So adaptive sampling and so on. And for learning, if you want now to learn some of these problems, that's a very nice setting as well. So in general, my group works all the way from modeling to the final user-friendly tool. And there are a lot of things we're doing. So as I said, we're improving the solution algorithms. We are trying to build these co-design games. And also we are trying to apply these tools to new applications, right? So mobility and autonomy is one, but we have a lot of things in aerospace, automotive. We just won a big grant with the Air Force on trying to optimize their multi-fleet design, multi-robot fleet design. So it's an exploding area. And if you go on our website, you will notice we do a lot of workshop, books, classes, let's say open material, really because we want to spread the word and first of all, get also to understand if we are missing something, if people have some critics. And second, also, we want to this language to be more used in the world. So if you go on with any messages, systems of today require new tools for their design and trade-off analysis. And I guess we have some way to deal with that, but we have more questions than answers so far. Again, this is great work from my students that I hope will manage to visit France at some point. We really look up to the quality of the French system. Actually, I have a student from Polytechnique joining in September, so really looking forward to that. But more importantly, I want to welcome more questions and I hope it wasn't too much out of time.